Some of the most devastating engineering failures aren't due to broken beams or collapsed columns, but to the ground itself giving way. For centuries, understanding this sliding motion or slip failure has been a critical challenge. We will explore one of the most fundamental and visually intuitive failure modes in geotechnical engineering, slope failure. Imagine a highway embankment after a heavy rain, or the catastrophic collapse of a dam's reservoir wall. Often, the underlying mechanism is a slip failure along a curved surface. In this session, we will also present the slip circle method, the classic analytical model that turns this complex soil behavior into a solvable engineering problem. We'll learn how to predict failure, calculate a factor of safety, and understand what keeps our slopes standing or allows them to fall. Let's begin by asking, what makes a slope fail? Let's start with the core concept. Slope instability is the downward and outward movement of soil or rock masses under the force of gravity. To analyze this, we need a common language. Think of a slope on the verge of failure. It's governed by a distinct slip surface, the zone where movement occurs. On this surface, two sets of forces are locked in a constant battle: the driving forces, primarily gravity, that want to pull the mass down, and the resisting forces, mainly the shear strength of the soil, that hold it in place. The outcome of this battle is quantified by a single, crucial number, the factor of safety, or FOSS. It's simply the ratio of total resisting forces to total driving forces. A value greater than 1 means stability. A value less than 1 means failure. Our entire goal in slope design is to ensure that this number is sufficiently above 1. Before we dive deep into one model, it's important to know that slopes don't fail in just one way. The type of failure depends heavily on the material and its structure. First, and the focus of today's lecture, is rotational or slip circle failure. This is a curved, circular surface, most common in homogeneous soils like clays. Next is translational failure, where a block slides out along a weak, planar layer, like a bedrock surface or a thin clay seam. In jointed rock, we often see wedge failure, where movement occurs along two intersecting planes. And finally, toppling failure, where slender columns of rock or soil rotate forward and collapse. So, why do we model this particular failure as a circle? Let's look at the basic principle. We assume the soil mass rotates along a circular arc. This rests on a key assumption, that the soil is relatively homogeneous and isotropic, meaning its properties are the same in all directions. In such materials, the failure surface naturally tends to be curved. From infinite possible circles, we search for the critical slip circle, the one with the lowest factor of safety. That's the most likely path of failure. But why a circle? For 3 good reasons. It's mathematically convenient, it closely approximates real failures observed in many soils and fills, and it allows for a systematic, trial and error analysis to find that critical surface. This elegant simplification gives us a powerful tool. Now, to understand why a slope fails, we must understand what tips the balance. The stability of a slope is governed by a complex interplay of factors. First, the geotechnical factors, the inherent soil properties. The most critical are the shear strength parameters, cohesion C and the friction angle phi dot. Equally important is pore water pressure, which can dramatically reduce effective stress and strength. Second, the geometric factors, the slope's form. Its height and angle, any external surcharge loads on the crest, and the overall slope profile itself. Finally, the environmental triggers. Rainfall that infiltrates and raises pore pressure. Earthquakes that add dynamic loads. Even erosion at the toe or removal of vegetation can be the final straw. Here is a typical slip circle problem. The failing soil mass is an irregular. Calculating the total driving and resisting moments for this complex shape directly is not straightforward. The elegant solution? The method of slices. We divide the entire sliding mass into a series of vertical slices. This transforms the complex geometry into a set of simpler, manageable columns. Now, we analyze the forces on each individual slice. Each slice has its own weight, W, a normal force, N, and shear resistance, T, on its base, and interslice forces from its neighbors. By making careful assumptions about these interslice forces, we can sum up the effects of all slices to get the overall stability of the entire slip circle. This method is the computational engine behind slip circle analysis.